It's recording. Okay, we're live. Today involves using what we've done before to build probably some of the most important identities we have ever done. You will need to know these identities in the future in order to do operations like differentiation and integration of different trig functions, especially ones that are squared. So I will be honest with you that the sum and difference ones, I can't think of a single time we've used those in calculus. They are pretty much done almost exclusively to first of all show you can get the 15-degree ones, but also to build these. So if we're going to go primo importance, this is about to escalate in importance, which means that most of my testing and like identities that come with this are going to be based on your ability to know, understand, and use these. So let's start with this one. Sine of twice an angle. The sine 2 theta identity pops up frequently. And it does so, and you can derive what this is by just saying that the sine of 2 theta is equal to the sine of theta plus theta. And now we're going to use the sum identity that we've already used. A clever way to do it. Sine theta cosine theta plus cosine theta sine theta, which actually does simplify to aren't these like terms? 2 sine theta cosine theta. That is the first of several we're going to do today. But this is one that you guys should commit to memory. This is also valuable because you actually have your first identity showing what happens when you multiply sine times cosine. Numerous times we're going to take sine times cosine and replace it with sine 2 theta over 2. So that's a way to kind of deal with sine times cosine and change it into something else. That's useful. Okay, let's derive the cosine double angle one. This one's a little bit not trickier, but it has more components to it. Cosine 2 theta can be expressed as the cosine of theta plus theta, which from our identities is the same as the cosine of theta times the cosine of theta minus what? And that's going to simplify to the cosine squared theta minus sine squared theta, which is also kind of revealing because if you're one of those curious people that ever wondered, we know what cosine squared plus sine squared is. What was cosine squared minus sine squared? Voila, this is it. And if you do sine squared minus cosine squared, you just have the negative of cosine 2 theta. I remember this because I remember that cosine of 2 theta means that cosine's first. And these two, I don't rederive every time. I commit these two to memory. So just straight up memorize the two of those. Now, the cosine double angle one has two other forms. The two other forms it has are because we can substitute either cosine squared or sine squared with the identities that we've done from the Pythagorean ones. Meaning, I know that sine squared theta is 1 minus cosine squared theta. That's a different identity. And I know that the cosine squared theta is 1 minus the sine squared theta. Hopefully you found it valuable doing all those little proofs so these can be in your head a little bit. So we're going to substitute and maybe set this all with cosines first. So I'm going to take this identity. I'm going to replace sine squared with 1 minus cosine squared. And just change things around a little bit. The negative's going to distribute. You'll get 2 cosine squared theta minus 1. So in addition to this being a form, this is also a form of the same identity. But as you might imagine, that's what happens when I substitute sine squared with 1 minus cosine squared. Perhaps I instead would have wanted to substitute cosine squared with 1 minus sine squared. So if that happens, I get 1 minus sine squared theta minus another sine squared theta, which leads me to 1 minus 2 times the sine squared of theta. And that is the third form. Which form do you think you need to know? All three. They all three will have their value, and they all three are different forms of the same thing. The first one is valuable in this can factor as a difference of squares. This is the one we're going to use to derive the tangent identity. And this is the easiest of all of them to remember straight up. I memorized this one, and then I memorized these two based on, well, they have a 2 in front of them, and which comes first? Cosine squared minus sine means 2 cosine squared or 2 sine squared. It's easy to remember the other two once you know the first one. But you do need to memorize and know all three of these. Okay, we're going to do the next two things in any order. I'm going to show you kind of problem types that you may encounter, and here's one. So you're going to have, this is common for books to do this, they ask you to say, now derive a formula for sine of 3 theta. This is not an identity you're going to have to memorize, this is an exercise in applying the formulas. How this plays out?
2 theta plus theta.
Yep, 2 theta plus theta. Which is then a recursive, repetitive, iterative application of the same identities. Trying to expand your vocabulary a little bit. Sine 2 theta, cosine theta, plus cosine 2 theta, sine of theta. And then bingo, we have these two right here that get to be substituted with their respective identities. Sine 2 theta only has a single identity, that is 2 sine theta cosine theta. And then we still have that other cosine theta that was just chilling there. Plus, I'll put this in parentheses so we can kind of corner that off and see where it comes from. Then we have this cosine 2 theta. You have three options of the one to pick. I'd pick the neutral one right now, the neutral one being the one that contains both a single cosine and a single sine. Cosine squared theta minus sine squared theta times a sine theta. Now let's distribute and kind of clean up, and maybe actually can we do a couple things at the same time? This will be great practice for what's coming in the next couple of years. Do this and this, these two purple underlines have a factor in common that I could pull out as a greatest common factor. Careful, this one doesn't have a cosine squared in common because this is cosine squared minus sine squared. They do have a sine in common. This sine right here and this one right here could be factored out as a greatest common factor. So I am going to do that. I'm going to pull the sine of theta out and see what's left behind. 2 cosine squared theta plus cosine squared theta minus sine squared theta. And the only other way to clean that up is just to add like terms. 2 cosine squared theta plus cosine squared theta is 3 cosine squared theta. And still minus sine squared. And that's about as simple as that goes. So there are many other ways you could express that. You probably could convert everything into sines, which if you had to pick, you would convert everything into sines because you have a sine theta out there. But we can leave it there for now. You've kind of reached an endpoint. So let's summarize. I like writing these identities down several times. Maybe use a lava color or something. Sine 2 theta is 2 sine theta cosine theta. Cosine 2 theta is cosine squared theta minus sine squared theta, or 1 minus 2 sine squared theta, or 2 cosine squared theta minus 1. Okay. Box these off. Vertical line down. And you know what? I'm being a little compulsive in my head. I'm thankful I skipped a space here. I do want to take this and convert it to sines, because a good rule of thumb is that if you're doing an identity with sine 3 theta, it should only be in terms of sines. 1 minus sine squared. It's okay, I'll try to do it all in one line. And that would be equal to sine of theta times, this would be 3 minus 1, so it'd be 3 minus 4 sine squared theta. Sorry, but that's considered a little bit better, because if you're doing an identity with sine 3 theta, it should be in terms of sine. Like, you shouldn't have to go to cosine if you're just doing a sine one. So yeah, okay, done. Guess what we're going to do now? I have sine 2 theta and cosine 2 theta. Be predictive. Tangent. We've did this before, where I'm going to take tangent, and we're going to use the previous 2 to get tangent, because tangent's just sine over cosine. So that's going to be equal to 2 sine theta cosine theta over, the one I'm going to pick of these is the neutral one as well. We'll just do cosine squared minus sine squared. Remember that discussion we just had like all of about 10 minutes ago about cheating? And cheating by making the numerator be what we want it to be. I don't want it to be sine or cosine. If it's an identity about tangent, it probably should all be tangents. So what can I multiply this numerator by in order to make it the tangent of theta? Well, 1 over so if I put cosine theta, it's going to multiply by the sine theta and get me tangent. That's good, but then there's still a cosine left over. So what do I need to multiply by? Think of it this way. If I do it right now, that's going to cancel. I still need another cosine, don't I? So let's do it again. Let's multiply by 1 over cosine again, or 1 over cosine squared. I'm going to multiply both the numerator and denominator by 1 over the cosine squared of theta. Because the first one will cancel that cosine. The second one will combine with this sine to give me tangent. In the denominator, well, let's go back to the numerator. That gives me 2 tangent theta. In the denominator, the first one multiplies and knocks that out and just makes it a 1. And the second one multiplies and makes it a tangent squared. And then, bingo, you have it all in tangents. Golf clap. So that's the tangent identity. We'll box that in and box that and pretend they go together. I don't know, the organization kind of works. So I was a little negligent in doing some examples until later, so we're going to do an example of this. And yet, you know, it's kind of tricky, because one of the first things that your homework tends to do, I wish I could flip over to it right now, is you do an example, and tangent 2 theta, well, let's just go sine. Let's say that I have, we want to do something with the sine of 2 theta, which means that I take an angle and I double it, and I'm taking the sine of that. Well, any angle that you know already, when it's doubled, it's still going to be an angle you know already. I mean, think about if I did the sine of, take an angle you know, give me any angle in degrees that you know to take the sine of. 60. We'll just go 60. Double it, you get 120. Isn't that another angle you know? These are not going to be used necessarily to find angles whose values you didn't know. They will be used in identities. So we'll get to that here in a second. Kind of backtracking, realizing, nope, there's a reason I did the half angle identities next. Okay, the next step, the next half of this, is the derivation of the half angle identities. The sine double angle one is used a lot. The cosine double angle one is used a lot. And here's another way the cosine double angle one is used a lot. This uses that the cosine of 2 theta is equal to the 2 times the cosine squared theta minus 1. And it uses that it's equal to 1 minus 2 times the sine squared theta. So this is a very real reason we use the other two.
What's that first word?
Uses.
Above that.
Derivation. So we're going to go with first Roman numeral. And we'll start with the first use of this. That the cosine of 2 theta is equal to 2 times the cosine squared of theta minus 1. So the value in this identity is that I now have a direct relationship between 2 theta and theta. I just told you that twice an angle is not as good of a thing to do. We already know how to do twice an angle. But can I use this to do half of an angle? The relationship between 2 theta and theta would be the same as the relationship between theta and what? 2 theta is to theta as theta is to half theta. Now all you have to do is algebraically get the cosine of half theta by itself. Fortunately, we know algebra. We're going to add 1 to both sides. And can we divide both sides by 2 right away? Can you guys handle that as a single step? I hope so. And then how do I get the cosine by itself if it's cosine squared? Guys, what's the opposite of squaring something? Cosine of theta over 2 equals, I know this instinct's building in with you, it's a plus or minus square root. But, and there's a big but here. The plus or minus, let's find it back up. Cosine does not output 2 values. It outputs 1 value. It's a function. It will not output a positive and a negative. But the positive or negative that is here, the plus minus, depends on what quadrant theta over 2 is in. That's it. So let's say that I have theta is, let's pick one. Theta is 81 degrees. Nope, 81 degrees is not a great one. Let's go 121 degrees. That's better. If theta is 121 degrees, is the cosine going to be positive or negative? Good. Is the cosine of theta over 2 going to be positive or negative? Positive, because theta over 2 is going to be about 60.5 degrees, or exactly 60.5. So just be wary of those two. There's theta, and then there's theta over 2. We're looking at actually taking the cosine of theta over 2. Theta over 2's cosine is positive. I don't know, that seems possessive. You do. And you will. You'll have a sense of exactly where they occur. You're going to use these in a variety of different ways. So this process right here, this is the next identity you guys will need to know. Cosine of theta over 2 is plus or minus 1 plus cosine over 2 radical. I'm going to be very upfront with you. I don't memorize that, except when we're in the middle of this chapter and I'm using this. If it's in calculus, I will walk them through the re-derivation from the cosine double angle one every time. So the number of times we do that comes down to it a lot. And again, the same thing I'm going to do with the sine. So let's go Roman numeral 2. I also established that the cosine of 2 theta was equal to 1 minus 2 times the sine squared. We're just going to walk through exactly the same thing with sine. If the cosine of 2 theta is 1 minus 2 sine squared theta, then the cosine of theta is 1 minus 2 times the sine squared of theta over 2. Same relationship. Now let's just isolate theta over 2. I'm going to switch things around and make it sine of theta over 2 equals 1 minus, oh, let's make it sine squared, equals 1 minus cosine of theta all over 2. I'm going to make this left side be clearer. So that's just some algebraic movings around, and then we get that the sine of theta over 2 is plus or minus radical 1 minus cosine of theta over 2. And like before, the plus or minus depends on what quadrant theta over 2 is in. So they look very similar. Obviously, there's like one difference between the sine and the cosine one. They both derive from the cosine's double angle identity, but this is the half angle identity for sine. I know, you're like all identitied out, and yet there's one more we have to do. Tangent. And we're going to do tangent by doing sine over cosine. So hang in there, Jess. Tangent, pi over 2, or theta over 2. We're going to go with tangent is sine over cosine, so watch how this is going to play out. I'm going to drop the plus minus for now, and we're just going to play it like it's tangent. We'll figure this out in a minute, so let's just put the radical down. 1 minus cosine of theta over 2 over radical 1 plus cosine of theta over 2. And now let's simplify. I can't drop the radicals. Please don't think we can just divide a radical by a radical and get rid of a radical. That's not how radicals work. But I can drop the over 2 part, because if I multiply the numerator and denominator by root 2, those are done. So this is just root 1 minus cosine theta over root 1 plus cosine theta. And that is a perfectly legitimate form of that identity, but it's not the only one. We've done enough of these trig substitutions to know that there's a better form coming. And let's do the better form. If I take this and I multiply this by root 1 minus cosine of theta under root 1 minus cosine of theta, in the numerator, the root goes away, and I get 1 minus cosine of theta. That's magical, but it's not as magical as what happens in the denominator. In the denominator, you get a difference of squares. 1 minus cosine squared. What is 1 minus cosine squared? Sine squared. And then in the radical, it's radical sine squared, so it's just sine. Isn't that neat? But it's not the only way. Right up above, I could have taken this equals 1 minus cosine of theta, 1 plus cosine of theta, and I could have multiplied this by, oh, let's pick purple. I could, instead of multiplying it by 1 minus in the radical, I could have multiplied it by 1 plus. Why would we do that? Because now in the numerator that becomes sine theta, and in the denominator it becomes 1 plus cosine of theta. Ooh, this is a mess. Which do we use? Let's summarize. And I'm going to box in the 3 that are really the identities that we're gonna have. But here's the summary. Sine theta over 2 is plus or minus root 1 minus cosine of theta over 2. Cosine theta over 2 is plus or minus root 1 plus cosine of theta over 2. Tangent theta over 2 is big root 1 minus cosine of theta over 1 plus cosine of theta. And I'll put a plus minus on that one because we'll have to determine what quadrant it's in. But if you don't want to determine what quadrant it's in, we have 2 more forms. 1 minus cosine of theta over sine of theta, or sine of theta over 1 plus cosine of theta. There you go. Wasn't that fun? It's okay. That's all the derivations for the day and for the chapter, but not for your life. we'll be deriving a lot of formulas. Remember what Mr. Keelan used to say. Don't drink and derive. So we're going to use the half-angle identity to solve for something that we otherwise wouldn't know how to do. You can do this with the sum identity, but you can also do it with the half-angle identity. Here's how it's going to play out. I'm going to take that, and if I'm going to use the half-angle identity, think opposite in your head. Use the half-angle identity, double that. What's double 165? 330. 330 is a friend. It's an angle you know. It's a happy angle. We're going to use the sine of 330 over 2 to make it become something we can work with. Now, substitute the sine half-angle identity we just did. We're going to put the plus or minus in because I'll make that determination at the end. I don't want to overload my brain. And I'm going to do 1 minus the cosine of 330 degrees over dose. The cosine of 330 degrees is a cosine you should know. Remember, it's a friend. It is 30 degrees off of 360 in quadrant 4. So because it's 30 degrees off of 360, and I'm sort of compulsive about labeling 1, 2, actually negative 1, root 3, I just want to make sure we get these right. Kidding. I just got them wrong, so I'm checked, and that's better. The cosine would be root 3 over 2. So I just want to make sure you guys get the math right on this. Please don't leave it like that. That's like an awful, awful form. We can clean that up a little bit. Namely, I can multiply the numerator and denominator of the fraction inside the radical by a 2 and make it plus or minus root 2 minus root 3 over. I'm going to separate this radical to make another point. Please don't leave it like that. Can I clean that up a little bit? Like the denominator, root 4. And then as a final curtain call, we're going to decide if the actual value should have been positive or negative. So to determine the positive or negative, and I'm going to write this down one more time because these are notes, and I want you to use these to kind of really, really help you to determine plus minus. Look at original problem. It's not nearly as hard as you think it is. Is the sine of 165 supposed to be a positive or a negative number? Where is 165? It's positive. It's quadrant 2. So we pick the positive one. Bingo. You don't have to put positive. I'm just picking positive. We'll say because 165 degrees is in quadrant dose, where signs are positive. Now I have a fun little exercise for you. This is totally optional. But we have learned that also the sine of 165 degrees can be calculated by doing the sine of 45 degrees plus 120. And if you were kind of thinking that, you weren't wrong. Anytime we have an ending in 5, I always just subtracted 45 and dealt with whatever was left. But this is the identity sine 45 cosine of 120 plus cosine of 45 sine of 120. And the sine of 45 was root 2 over 2. The cosine of 120 degrees is a 60-degree angle in quadrant 2, so that's negative a half. Cosine of 45 was root 2 over 2, and the sine of 120 is root 3 over 2. So if I finagle this around and simplify it a little bit, I get root 6 minus root 2 over 4. So which is correct? Which of the two of those is correct? Because I just did this problem 2 different ways. They're both correct. If you were to plug those in your calculator and do an approximation, you'll get the same decimal value. So what do you think my optional little funness is going to be? What? Prove that they're equal. Totally optional, and I get takers every year. Look, I'm not trying to say that I'm writing your college letters of recommendation at some point, and that this kind of curiosity is something that plays into. I'm not saying that. No. I'm just saying that there has to be a part of you that is curious about, do you possess or can you accomplish the mathematical skill to show without crossing the streams that the two of those are equal to each other?
Alright.
Okay? Do not cross the streams.
Oh.
Do not distribute a radical across addition subtraction.
Take the root 2 out of the right side.
Okay, again, but you've got to make sure that you can distribute, or that careful, just, if you see things, great. If not, but just be really, really careful that what you're doing is mathematically equivalent. There's a number of ways to show this, but remember, you've got a result with one side completely equaling the other side. Okay, good luck. Totally optional. Let's move on to a problem that's not.
Well, we gotta do this. We gotta figure this out.
Not right now. You can get to it in a minute. We'll put optional because Haley and Carly can be like, what? If the sine of theta is equal to 1/5, and the cosine of theta is equal to 2 root 6 over 5, find the sine of 2 theta. Here's a 2 theta problem. It's not a hard one, because what's the identity for sine 2 theta? 2 sine theta, cosine theta. This is just a direct substitution. 2 times 1/5, 2 root 6 over 5. Multiply, and you get 4 root 6 over 25. Done. Okay. I'm going to give you guys the greatest gift I can with the last 5 minutes in class time.